push away from pain. Hand on the bottom, it's a safe little family. Surrealistic fantasy, flamboyant. Hold me now, it's restitution. Living out your day to future. It's the whole place, shining past. Don't be guilty, master right. Somebody said that they're not much like I am. I know I can make enough of the words you go along and sing a song. Pessimist, hungry, domestic, conservative, communist, apocalyptic bastard. Thinking it God, putting me on this earth. They very privileged, depth of my thirst. Only now is restitution. Living out your day of fusion. Is the whole place in the past. Don't be guilty, that's the right. Somebody said that they're not much like I am. I know I can make enough of the words you go along and sing a song.
Okay, so we were looking at a pre-order traversal last time. In fact, we implemented a recursive version as well as a stack-based version. That ultimately what we did with it is we put it into an iterator pattern so that you can actually use it in an enhanced for loop in Java. So if you remember that an iterator pattern is required for your assignment 7 next week, but you do not have to necessarily use a binary search tree or a binary tree or anything like that. Instead, you can write an iterator pattern for a linked list or an array-based list, right? So what I want to do now is take a look at the other details of the other traversal strategies. So remember, for traversal strategies, right? What we had was a pre-order, which we focused on, right? That's going to be a root left, right ordering. We also have an in-order traversal strategy, which is just simply doing the left before you do the root, and then you do the right. And then finally, you have a pre-order traversal. That pre-order traversal is simply taking the root and saving it for last. So you're doing left, then right, then root, right? And we went through examples of each one of these. In fact, I had you do them. What I want to do now is I want to show you what they look like over here in, say, pseudocode. So with our stack-based pre-order traversal, we created an empty stack. We pushed the root, and then we went through while there was still stuff to process. We popped it off, and then pushed the right child and the left child. For doing an in-order traversal, it's going to be a little bit more complicated, right? In fact, here it is. Why? Because you need to determine where you came from. Did I come from my parent, in which case I'm not going to process that node until after I've done the left child. So I save it off, right? Because this is the first time that I've seen it. And then the next time that I see it, that's when I process it. So you need to determine, is this the first time that you've seen it or the second time that you've seen it in order to determine whether or not you should process it for an in-order traversal strategy. Jumping ahead here to a post-order traversal strategy, it's even more complex. Why? Because you need to distinguish three things. Is this the first time I've seen this, the second time I've seen this, or the third time I've seen this, right? And the full details are here. We're not going to translate this into Java. Instead, what I want to do is give you the intuition behind this. So there's the tree, but let's take a look at more generally here, that if I'm at a node U, right? Well, I'm connected potentially to my parent unless I'm the root. I'm connected to a left child and a right child, okay? What I need to do is I need to keep track of, did I come from my parent, right? In which case I need to go down to the left child and process this node if it's a pre-order traversal. Or am I coming back from my left child? Or am I coming back from my right child? I need to distinguish between those three cases. So all we have to do is write out the rules, right? You are at node U, right? If you came from P, or L, or R. Go to, dot, dot, dot. Well, if I came from my parent, where do I go to next? Forget about the processing for a second. I go to the left child before I go to the right child, because I go to the entire left subtree and then I eventually return from it. So I go to the left child. If I am returning from my my left child, then what I need to do is I need to go down to the right child, if it exists, of course. So R. And then finally, if I'm returning from my right child here, where do I go? I go back up to my parent so I can explore the rest of the graph, or rest of the tree. So P. Right? Those three simple rules. Where did you come from? I'm at you, but did I come from this direction, or this direction? That determines where I go to next. It also determines the processing order. And process you if dot, dot, dot. Well, if I came from my parent and I'm about to go to my right child, if I want to process you, that would give me a pre-order traversal, right? Before I go to L, excuse me. If I came from my left child, before I go to my right child, like it says here, then I process you if it's an in-order traversal. And by process of elimination, guess what? A post-order traversal occurs if you're coming back from your right child, because I've already gone down and explored this. I visited it once, clear that, once, twice, thrice. This is the third time I've visited it. And if it's a post-order traversal, that's when I do it. You only need to keep track of these three simple rules. This pseudocode over here is more complex because you need to keep track of corner cases. What happens at a leaf? What happens if there's no left child? What happens if there's no right child? What happens if if you're at the root, right? And so that's what all of these are doing right here. And also half of it is just comments telling you what I'm doing here. Instead, what I'm going to do in Java is I want to adapt our recursive solution. Let's come over here and take a look at our recursive solution for a pre-order traversal. Right? There's the pre-order traversal. What would it look like to change that to an in-order traversal? In order. Right? Well, first of all, I've got to change the names there. Right? An in-order traversal will recursively call in-order and in-order. When do I process the node? I don't process it before I process the left and the right child. I process it where? In the middle, right there. What would a post-order traversal look like? Post. Again, change the names, change the names, change the names. Oh, sorry about that. Oh, hopefully, just a second. Okay, there we go. Sorry about that. Let me go ahead and try to fix it. The screen is frozen on the live stream. Let me try to fix it really quick. Classroom. And there we go. Okay. Transition that. I mean, it's changing over here, right? So but on the actual live stream, it's frozen. And I'm not frozen, but the screen is frozen. So hopefully that changes. There we go. All right, it's coming back. There we go. Sorry about that. Here are the graphics that I was drawing. Right? There we go. So this is also in the book. You can review the book here as well. That if you're coming from the parent, if you're coming from the left child, if you're coming from the right child, you have these rules where you go there, and then you've got these pre-post order and in-order traversals. Right? There we go. All right. So over here, though, what I was doing is I cut and pasted the print in order, recursive, in order. There's post order, post order, post order. And where do I process it now? I process it after I've done the left child and the right child. Right? Hopefully that is working. Okay. All right. All right. So let's actually test these. Sorry, that's what we should do next, right? So I'm not going to use my enhanced for loop here. I'll save that for later, though. But what I want to do is I want to change this from a pre-order traversal into an in-order traversal. Right there. LGRMNDB. I don't know if is that correct or not. What's one thing that I could take a look at, right, with respect to this tree? I do know that A should appear right here after all this is done, and then all this should come after A. So C, F, J, P, Q, and K should come after A. And let me increase the size here. There's A. C, P, Q, J, F, and K are all after it. Right? So it looks good. Right? What if I were to do a post-order traversal? Right? I don't have them up, but we did these maybe 2 classes ago. I forget when, but there it is as well. Sanity check there. A should be last, right? Because it's a post-order traversal. The root node here is going to be last. But there are the number. There's the order of each one of these. I only did it because it was so easy, right? Generally, I advise against recursion, right? This is one of the times that I would say that recursion has something going for it, because the big difference between a pre-order, in-order, and post-order traversal is just simply where you put this line of code. Right? Do you put it first, second, or third? And you get completely different applications for each one of these. What I want to show you is yet another traversal strategy. Right? What I want to do is I want to read this thing top to bottom, left to right. Right? In that case, it's going to be a breadth first search. Breadth first search. In other words, it's just going to be A, B, C, D, E, F, G, dot, 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 your regular ABCs. Because I'm going to be starting at the root, and I'm going to read each depth left to right. Remember that each one of these has a depth of 0, 1, 2, 3, 4, and 5, respectively. Right? Each level there. This is called breadth first search. I'm not going to draw it again. I'll use this that I did last time here, or from the last section. Because if you have a missing person and their last known location was right here, and maybe they wandered off in this direction and you have an idea that of which direction they went in, well, then you go after them. But if you have no idea where they went, right, but you know that they're in this area, what you do to search is you set a perimeter here of, say, radius 1, right, whatever that means, 1 kilometer, 1 mile, whatever. And then you search in that entire area first. Why? Because the idea is that they couldn't have gotten far, right? If you've exhausted your search around this area, then you expand your search to a radius of 2, then a radius of 3, then a radius of 4. Why? You're cautious about it because each time you increase your radius, right, pi r squared, you are increasing your area by a factor, by a quadratic factor, right? So each expansion is more and more expensive. And so that's what we're doing here, right? What we're doing here is we are being cautious about it. We're looking at things that are distance 1 or depth 1 from the root node, then distance 2, then distance 3, then distance 4. This is just a different way of doing it with its own applications, okay? How do we go about doing it on this example, though? I'm going to draw you another data structure here that everybody should know what this is. Right? I'm going to start at the root here and put it in here. I'm going to put things in this one end, and I'm going to take them out in this end. I'm going to keep track of the current node. And so when I pull this guy out here, right, I'm looking at A. I process A. So now A is done. Then what I'm going to do is I'm going to take its left child and its right child, and I'm also going to put them into this data structure in that order, left, then right. Then I'm going to continue. I'm going to take that out of the data structure, replacing my current, process it, so now we're on B, right? And then I'm going to take its children, left child first, then right child, D, then E, and I'm going to place them into this data structure. Right? I'm going to continue to do that until I've explored left to right, top to bottom. What is this data structure again? It's a queue. Let me show you what it looks like over here. There's a pre-order traversal strategy. It's going to be exactly the same. Right? Remember, this is called BFS, breadth first search. Right? You can get into holy wars on whether or not you should be lowercase fs or uppercase fs. Why? Because there are only 2 difficult things in computer science. One is cache invalidation, and the other is naming things, right? So when you've got an acronym in your function name or in your method name, do you follow the same rules? I generally do, right? just to be pedantic about the rules. Yes, it's an acronym, and yes, it should be like this, but no, it should not be like this. Breadth, first, search, traversal. That's icky. Any computer scientist is going to know what BFS is. Right? All right, well, if the tree is empty, then we just print empty. Otherwise, we're going to create not a stack, but a, what was that thing I circled again? A queue. Right? I'm just going to go ahead and right-click, refactor, rename, queue. Right, there we go. So it's still a deck. Why? Because a deck is a double-ended queue. You can treat it like a queue, or you can treat it like a stack, or some combination thereof. I'm not going to push anything. I'm going to offer it. Enqueue is offer in Java, so enqueue the root. That gets me started. While the queue is not empty, I'm not going to pop it. I'm going to pull it, right? That is dequeue, right? And I'm not going to go left, right, left. Instead, I'm going to go left, right, because I want to read it left to right, not right to left. And a queue is a first in, first out data structure, not a LIFO data structure. All right, not push, but offer and offer. There you go. It doesn't matter if I process it down here or up there or whatever. Right? It's going to be the same order. Let's go ahead and print this out. And if this is correct, it should be absolutely clear what it should be. A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, right? And it is. A, B, C, D, E, F, G. All the way down to R. Right? Cool. What's the difference? So here, let's look at the pseudocode. The pseudocode for a pre-order traversal. There it is. You create an empty stack, you push the root. While that data structure is not empty, you pull something out, you process it, you push the right child, left child. What's the only difference here? I'm using a queue instead. And of course, I'm going left, right instead of right, left. But otherwise, exact same code. So remember back at the beginning of this course, there was a theme that I wanted to establish for this course that we're getting there. That it's a quote by Eric S. Raymond that smart data structures and dumb code are a lot better than the other way around. This is dumb code. Put stuff in, take stuff out. Put stuff in, take stuff out. Using a queue gives you a BFS with its own applications. Using a stack gives you a pre-order traversal of a tree, which has its own applications. All you have to do is change the data structure. It's the same stupid code. It's the same dumb code. Put stuff in, take stuff out. But it makes a huge world of difference. We've seen this already, right? Not in this module, but in the previous module. I started out by showing you, hey, here's a linked list. Here's an array-based list. Here's something that takes 20 years on this version that we've sped it up to only 3 seconds on this version. Right? The only difference there was what? The data structure. Right? Smart data structures, but you got to know when to use them and when not to use them. Right? I will mention BFS here, which is breadth first search. Right? What about efficiency? So if your elementary operation is, say, processing a node, printing it, pulling out its data and looking at it to see if that's the thing you're looking for, whatever you're doing with it, right? Then it's going to be order n. Why? Because every node is processed exactly once. No less than once, no more than once. Right? If your elementary operation is something else, what would you say? Think back to linked lists. What was our elementary operation there? I wanted to find something in the linked list, right? Or an index-based search. I wanted to find the 50th thing there. If it was an array list, I could simply jump there, and it was order 1. But what about a linked list? The painter and the paintbrush and walking back and forth for the fence, traversing those nodes. So if the elementary operation is a node traversal, do we have any different behavior? Let's look at this diagram again. This one right here. That was not on the live stream, sorry. All right. How many times do I traverse this node U? Once when I come from the parent. Twice when I come back from the left child. Thrice, third time, when I come back from the right child. So I make at most 3n node traversals, right? At most there are 3n, which is still order n node traversals, node or edge traversals. So it's still going to be linear. The catch is that these are designed to traverse the entire tree. That's not what I wanted. When we started this process, what I ultimately wanted was an efficient data structure with the potential for all efficient operations. If this is no better than a linked list, right? If you have these elements and you stored them in a linked list and say J was what you were looking for, and it was the last place that you looked for, it'd still be order n. J is still order n because basically I have to explore this entire subtree to get over here to finally find where J is. I only end up skipping a very few number of nodes here. And in fact, if I were searching for, what's the last thing in the pre-order traversal going to be? K? If I were searching for K, I would end up comparing it to all of the nodes. I would really like a world in which I can go to A and I can ask the following question. I'm searching for J. Are you J? No, I'm A. Oh, I'm sorry. Where's J? Is he down to the left corridor or is he down to the right corridor? And A would be able to answer, oh, he's down in the right corridor. You don't even need to explore this thing, right? I know that he's not in that part of the maze. He's over in that part of the maze. So I come down to C and I ask, J, I'm looking for J. Is he in the left corridor or in the right corridor? Right? He's not in the left corridor because it's empty. Okay, I'll go to the right corridor. I ask F, where's J? Is he in your left corridor or the right corridor? And he says in the left corridor. And so I was able to make 1, 2, 3, 4 comparisons. For that, we're going to need more structure. Right? And that structure is a binary search tree. Right? We already have binary trees. A binary search tree has more structure. Right? Because generally, we store elements in a tree node. We can also store additional structure on that data so that it's ordered. Right? In a binary search tree, right, you store both data and a key, right, element. Right? Then you have the BST property. Right? Every node, for a node with key K, every node in its left subtree has a key value less than K. Every node in its right subtree has a key value greater than K. Right? So there's now some practical issues here. Practical issues. Right? For our purposes, we'll keep the data and key the same. Right? They will be integers, right? And they will be unique, right? Distinct. There we go. Key. There we go. Why is it okay to restrict my consideration to this? Well, because you can always separate it, right? You can always keep track of two things, right? I'm only going to keep track of one thing because I just want it to be simple for this, right? There'll be integers. Why is this a good restriction? Because at the end of the day, every object can be given an integer representation. How? Here's my person object. It has an address and emails and sales and all this other stuff conceptually. But at the end of the day, it's on a computer. And a computer thinks in zeros and ones. A bunch of zeros and ones, you can treat that as a number. That number can be an integer, right? So does anybody know anything about export controls or munitions? So it used to be, for example, the PS3, when it first came out, it had chips so powerful that they were classified as munitions. And you could not export PS3s because they could be used in missile guidance systems, right? And so there were restrictions. Of course, they were outdated restrictions, and then they finally were lifted. It used to be that software was treated as a munition. That if it had a military purpose, you could not publish your software outside of the United States. And so the way that they broke this and finally took the system down of this munitions, software as munitions, is that they said, well, technically, numbers aren't munitions. Numbers can't be weapons. So what I'll do is I'll take my source code, and I won't publish my source code. Instead, what I'll do is I'll encode it, right, as a bunch of zeros and ones. And then I won't publish the binary. Instead, what I'll do is I'll take, oh, those zeros and ones, those can be treated as big giant numbers. And here's my program. It's just one integer number. I'll go ahead and publish that number. Right? And that's how they got around it. Right? The guy that made PGP, Pretty Good Privacy, that's what he did. He took his encryption software that offered encryption to folks, and he just published it as a single number. Right? Here's my software. Right? And then once you took that number and you decoded it properly, you got all the source code. Right? And so that's how they got around that. Right? That's why this is an equally good restriction. Right? Everything can be an integer. Anything can be an integer. In fact, in Java, you do this using the hashcode method. In Java, you use the .hashcode method. Right? It returns an integer, right? Which is an integer representation of that object. Why is it okay that they'll be distinct? You can always break ties somehow. All right? I've got two identical people, John Smith, John Smith. Right? They have different social security numbers. That's how I'll break ties. I've got John Smith, and they have the same social security number. Maybe I don't want to make a distinction. No, I'm going to collapse those into one object. Or I'll say, okay, well, no, they are distinct things in memory. So the memory address of that one comes before the memory address of that one, so that's how I'll distinguish them. You can always break ties somehow. If something has the exact same data and is stored in exactly the same place in memory, it's exactly the same thing. There is no tie there, right? Okay, so those are the practical issues. Here is the conceptual visualization of a binary search tree. If I have a node, K, and everything over here in its left subtree is going to have, come on. There we go. I just want a simple triangle, not a right triangle. There we go. Everything is going to be less than K over here. Right? I have another subtree over here where everything is strictly greater than K. Right? Now, how does that help me? Let's look at a full example. This is the same topology as before, the same tree, the same shaped tree, but with the letters being replaced with numbers. Right? Now, what if I wanted to search for, say, let's go 24. Right? Let's keep track of the number of comparisons to do that. Because this is a binary search tree, I can go to 50 and I can ask, are you 24? No, I'm not 24. I'm 50. 24 is less than me, so where would I go? To the left. I ask 40, are you the thing I'm looking for? 24, no. 24 is less than 40, so I go to the left again. I ask 20, are you 24? No, I'm 20. 24 is greater than me, so I go right. And I end up at 24 right here. A successful search having done how many comparisons? 1, 2, 3, 4 comparisons. Now I don't know how many, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 nodes overall. If I used a pre-order traversal, post-order traversal, in-order traversal, whatever traversal, right, then I would end up exploring potentially the entire graph before I get to find the one that I'm looking for. Here, however, I only need to make 4 comparisons. Let's do another example. What about 12? Less, 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 greater, less. How many comparisons did I make in that case? 1, 2, 3, 4, 5, 6. 6 comparisons. What if I search for something that was shallow in the tree? 50. There I'm going to get lucky. I only need to make 1 comparison to see that the root is what I'm looking for here. Right? What about, I don't know, 72? Right? You do have to be careful. Not everything is going to be in this tree. Is 72 in this tree? Nope. How do we know that? We ask 50. We go down to the right, go down to the right, go down to the left, left. And if it were there, it would be right here, but it ain't. We made 1, 2, 3, 4, 5 comparisons here to see that it was an unsuccessful search. How many comparisons are we going to be making in general with this tree? Do you see the pattern here? Sometimes you'll get away with fewer, but sometimes you'll end up having to make 6 or 5 or 6 comparisons. Given the topology of this tree, remember what's the depth of this tree? There's depth 0, 1, 2, 3, 4, and 5. Right? So if the thing you're searching for is at the very depth of the tree, then you need to make that many comparisons. Right? In this case, I guess in this case, +1. Right? So, in general, there are let me put it in the notes instead. Right? To search requires at most D plus 1 comparisons. In other words, order D. Now, why is that significant? Let's come back up here. Do you remember how we can exploit this structure? If we can get a nearly full binary tree, then we have a guarantee on the depth. D is going to be order log n. In which case, we can perform these operations and they'll all be efficient. Right? But is that going to be the case? That's kind of balanced right there. It's almost full, but it ain't full. Let me give you a worst case scenario example. 10, 20, 30, 40, ... 100. Right? There we go. In other words, everybody has a right child, but nobody has a left child. No left child, no left child, no left child. First of all, what's the depth of this tree? Remember, this is 0, 1, 2, 3, ... There, so, oh, careful. I started at depth 0, so this would be depth 9. 9 in this case. Or in general, D is going to be order n, which is no better than, hey, that looks familiar. Say what?
Linked list?
No better than a linked list. Why? Because what is that thing? It's a linked list. Right? So, no better than a linked list if we have a degenerate tree, a tree where there's only right children and no left children for whatever reason. Right? So it can devolve, right? Generally, we don't have that luxury to assume that you're going to have that depth, right? However, the depth is not guaranteed to be order log n. Right? It can be D is order n in the worst or degenerate case, right? Unfortunately. So we're not quite there yet, but we will eventually be there. In fact, let me give you, we won't get there fully for this course, but let me show you an example here of what you might see in, say, Computer Science 3. It's a balanced binary search tree. And what happens is, suppose something gets unbalanced. Suppose that you have, say, 30, 20, and 10. That's unbalanced. Why? Everybody has a left child, but nobody has a right child. Nobody has a right child. So what I want you to do is imagine that this is a chain, because it's kind of a linked list. They're chained together. And that it's sitting on one side of a hill. Right? So this is a hill. Right? And then there's a guy over here that has access to this, and he starts pulling in that direction. Right? In other words, he pulls around this hill right here. Right? What is the resulting tree look like? It ends up looking like 20 is at the top, 10 and 30. Right? In other words, it's been rebalanced. Right? Now, everybody has a left child, everybody has a right child. And this is just a simple 3-node tree, but you can do it on a general node tree. All you need to do is rebalance it by, this is called a rotation. Right? And there are several other types of rotations. For example, if it were skewed this way, you would pull it that way on the hill. If it were skewed zigzaggy, right? So, I don't know, 20, nope, what do I want? I want that, that, and that. So I want 10, oh, I don't want 10 over there, sorry. 10, 30, 20, there. That is a binary search tree, right? Verify, right? Everything in the right subtree is greater than 10. Everything in the left subtree here is less than 30, so it's 20. And what you do is you do this twice. You drag it over one hill here, and you drag it over another hill there. Right? In the first one, you end up with 10, 20, and then 30, which guess what? Is just one of these rebalances up here. Because in the second part, you drag it that way, and you end up with 10, 20, 30. So if it's zigzaggy like this, then you just need to zigzaggy rotate it. Right? These are called AVL trees, but they're not the only type. There are red-black trees, there are B trees, there are 2-3 trees, which is a special case of that. There are a whole bunch of different types of trees that rebalance themselves in order to give you this guarantee. Right? They will guarantee that the depth is always going to be order log n. And therefore, all of the operations are going to be order log n. Right? What I want to do with the remainder of our time here is I want to develop at least that search algorithm. Binary search tree search. Right? So my input here is going to be a binary search tree, BST, T, with the usual root and a key K. And my output is going to be an element in T, such, here I'll call it X, such that X is equal to K. Right? Basic search, right? This is the same thing as linear search or binary search, right? Except that the input here is a binary search tree instead of an array or a collection or something. And we're going to output a node or the data in that node such that it matches the key. Yeah, here we go. All right. Remember how this search works. I start at the root. I'm going to ask, are you the guy that I'm looking for? Right? I'm going to say, if X is equal to the current key, then I'm done. Right? I found what I'm looking for. Otherwise, if the thing that I'm looking for, the current K, right? Otherwise, the thing I'm looking for, K, is less than the current key, then where do I go? Left. Otherwise, if the current key is greater, or is less than the K, the K is greater than the current key, then I go right. When do I stop? When did I stop for 72? Right? When I fell off the edge of the tree. So that means over here in my pseudocode, I'm going to keep track of the current node. Current. I will initialize that to the root. And then I have a while loop. Why did I say while loop? Because I don't know how far I'm going to go. Sometimes I get lucky, and I find it right away. Sometimes I don't get lucky, and I don't find it at all, right? So I'm going to do a while loop here because it's more natural. While the current node is not null, my placeholder for null will be phi because this is pseudocode. I need to check, is this the thing I'm looking for? If current dot key is equal to K, the thing that I'm searching for, then done, output, current dot data or whatever. Okay? Else if the thing I'm searching for, K, is less than the current key, then I need to traverse left. To do that, I will update my current to be current's left child. Else if the current key is less than the thing I'm looking for, that means that the thing I'm looking for, K, is going to be in the right subtree, and therefore I update current to be current dot right. Once I get done with this while loop, if I still have not found it, then I output what? Null or phi in my placeholder, phi if no such element. Right. There. It's a basic while loop. Do we have time to implement it? We can try. Where's my, I did not have a, oh yeah, there's my Eclipse. Right. Now my first question here is going to be, should I modify the binary tree or should I create a new one? New class binary search tree T. There we go. Now wait a second, I've got a whole bunch of stuff over here that I put a lot of work into, right? I put a lot of work into having a pre-order, in-order, post-order, and an iterator pattern and all that stuff. I don't want to lose that work. Let me go ahead and extend binary tree T. Why might that not be a good idea though? Yeah, right? It doesn't necessarily make a lot of sense. What does a pre-order traversal on a binary search tree give you? Nothing meaningful. What does a BFS, breadth first search, provide you on a binary search tree? Nothing meaningful there either, right? So no. One way that you could do this is you could use composition over inheritance. We've done this before. You could have private binary tree, right, T, if you wanted to. I'm not going to do that though. I'm going to start from scratch. I'm going to have a tree node and a size over here, right? And then I'm going to take care of everything myself, right? Because I want a complete and separate, distinct implementation here. Right? Ultimately, I don't want a class called binary search tree anyway, because I don't want you thinking that you can have access to those nodes. And that you can think about, that you require you to think about roots or anything, or anything else like that. I want something that looks like just a generic collection. Put stuff in, take stuff out, put stuff in, take stuff out. So ultimately, I'm probably going to rename this into a sorted collection or something, right? And it's a binary search tree implementation though, right? Okay. Again, you don't have to use a binary search tree on assignment 7. We're expecting linked lists or array lists. Right, but if you want to go the full 9, then this is how you do it. Public binary search tree. There we go. This dot root is equal to null. This dot size is equal to 0. Another argument against extending it is you can kind of get into the Liskov substitution, or a violation of the Liskov substitution principle, like we did with people and directors and authors. What happened when we had that one special person that was both, right? Were they this or both or neither, right? It locked us into a hierarchy that I don't want to be locked into here, right? Maybe later on I'll say, okay, well, it does make sense to lock this into a hierarchy and I'll redesign it, but for now, let's just go ahead and design it independent. Public, void, add element of type T, right? To do. Right? I need to get stuff in there somehow. Public T, find T element. Right? There we go. We're probably not going to be able to complete this, but let's go ahead and at least try to translate the pseudocode over here. Right? What's my first step? Is to create a tree node, current, and assign it to this.root. That's step 1. While the current is not equal to null, you make these 3 checks. While the current is not equal to null, then I'm going to check down here. If I break out of this while loop and I never find what I'm looking for, then I'll return null. Right? If cur.getElement is equal to element, then I found what I'm looking for. Return cur.getElement. I'm not sure about that. Else if cur.getElement is, let's translate it like I did over here. So if the key element that I'm searching for is less than, in fact, let me call this key to make it more explicit. Key, if that's equal to my key element, if the key element is less than the current element, then I need to traverse left. So cur is equal to cur.getLeftChild. Else if key, the current element, cur.getElement is less than the key element, then I need to traverse right. Cur is equal to cur.getRightChild. That ain't compiling. And in fact, this was wrong also. This equals. First of all, why is equals wrong? What does equals compare in Java and in C? memory addresses. Right? And is that checking to see if that person is the same person as that person because they have the same UUID? No. Likewise, it's not even going to compile if I try to use the usual less than, greater than. We don't have time to do it, but you tell me, what's the solution? Comparators, right? Oh, we have time to do it now that you gave me that really quick answer. Private comparator. For what? Comparing elements of type T. I'll call it CMP. Right? I need to import it. There we go. And I'm going to require you to give that to me at instantiation. You're going to have to tell me how to order elements of type T. This.cmp is equal to CMP. CMP is a terrible name, but whatever. Now how do I test for equality? I don't know anything about those elements. Are they strings? Are they integers? Are they people? Yes, all of those things. Compare the current element and the key element. Right? And if the comparator says that that's 0, then that means that they're equal, and that's when I return that element. If the comparator is comparing the key element, put that first, just so that I have the same order here, and that is less than 0, there we go, it's balanced now, then I go left. Otherwise, if I compare that and it's greater than 0, then I know that I need to go right. Right? It all compiles, right? And it's all generic. Right? I can create a binary search tree for strings, for integers, for whatever. And all I need to do is give you a comparator that tells you how to compare those things. I could have a binary search tree that had a bunch of integers and it ordered them in ascending order, and then I could reverse that comparator, and now it's going to order them in descending order. Right? I don't have to worry about any of those details anymore because I'm using my comparator here. Right? I don't have an example to actually run this on, but we will develop one next week. Right? All right, so have a good weekend, and final 2 weeks of class here coming up.